In this lecture, we're going to really exploit everything we've learned up until now and look at agent-based models and as an example of how we can do very complex simulations using the notion of render to texture and everything else we've done. Although the examples we'll do today are two-dimensional just to keep them a little simpler to explain, everything we do works very easily in 3 dimensions and could lead to some wonderful projects for the class. So the ideas here are we want to talk about using WebGL for simulation and using render to texture to get the sort of dynamic visual simulations you can get using agents, which we can think of as particles. So this is an example of particle systems where the individual, we call them agents because each of the particles doesn't have to have exactly the same behavior. There was no reason in any of the code that we've looked at so far that each point, or even if we're talking about geometry, each geometric entity, we could have a whole bunch of triangles, each of which could have its own particular behavior, and they could also, as we'll see, interact with each other. So here's one example right off of diffusion, and let's look at that because we're going to be using diffusion a lot. So here's some examples that I have on the website for the class. Let's look at this one here. Let me restart it here. So this is a bunch of randomly moving points. Now, there's nothing here that's particularly different from anything that we've done thus far. All I've done that's slightly different is of these, I think there's 100 points here. I have first 50 of them are colored green, and the next 50 are colored magenta. And as they move around, kind of randomly, they're leaving their positions in the texture, and that's being diffused by the shaders, so you could see the colors kind of fading away. You could also see where there's both magenta and green. The sum of them is a kind of generally a gray if they have the same strength, and so they generate these very beautiful patterns that you're seeing. So what's been added is that the particles are different from each other, but they're not really interacting with each other here, and there's nothing very dramatic happening. But I think this is, you can see that there's the potential that, well, if I can change the color, I can change other things. So let's talk then about agent-based modeling, and we'll look at the code and we'll come to some more complex examples. But this one, I think it really has all the elements that we're going to use or need. Okay, so let's move back here. Okay, so render to texture and agent-based models are based on this kind of idea that we have a particle system. So we're going to talk about particles that move around, but they could have their own properties. For example, they can have different colors. And also key to this notion of particle systems, which is used not only for simulations of physical properties. For example, they're very popular as a numerical method for replacing solving a partial differential equation by rather doing it by simulations where you inject a particle into the system and look at its behavior. And if you do this for thousands or millions of particles, you wind up getting the same result as you would have gotten by solving some complex partial differential equation. They're used in the animation industry all the time to do things, for example, like crowd scenes, that you model each person as being a particle to get the interaction and how they move around and how they avoid each other, but then you can render them with different geometry. So we separate sort of the dynamics of what's going on from what we actually render in the end. And then agent-based models are another example of that, where we're doing simulations of other kinds of phenomena. For example, well, we'll see one in a minute of ant behavior, but another one that's very popular is to do predator-prey problems, where you have two different kind of particles, one which might represent rabbits and the other might represent foxes, and they move around, and if a fox sees a rabbit, it eats it, and then you can, if the foxes don't find rabbits, then they die off and get eliminated. So you have a bunch of rules that affect their behavior, and so they're interacting both with the environment. In the case of something like a predator-prey problem, the rabbits have to eat grass, and so the environment, the background in in the graphical sense could be represent grass, and so you have sort of this complex interaction going on between three different entities. And so let's look at another example here before we look at the ones we're actually going to have the code for. This is a very famous one, and in a way the simulations that I'm going to show you come very, very close to this one. So suppose you have ants that are going around and looking for food, and you can sort of see this in the world war. They sort of move around kind of randomly looking for food, and when they eventually find food, all the other ants manage to go along the path that that ant that found the food traveled. Now, how did that happen? Well, it happened because they left traces called pheromones there that other ants can detect and then move. That's kind of the diffusion onto the background, because over time the pheromones will disappear, but if while they're strong, other ants can follow them. And then we can put certainly much more complex behavior in here. What happens if, well, you have two different kinds of ants and they don't get along? What happens if they cross paths and they eat each other or something like that happens? So you can put on multiple layers into this simulation. It's also very clear, I think, that whether this is two-dimensional, as I'm going to show you, or three-dimensional, where they move along a surface, that really isn't much different. So not only can we render each point with some arbitrary geometry, if it's an ant simulation, then for each point you eventually render some geometry that looks something like an ant. Also, I should have mentioned a few minutes ago, this is goes on in games all the time. That the behavior of all of these different agents moving around in a game is very much a particle type simulation, where you, the player, are another particle in some sense, but you're controlling your own behavior while these others are acting according to some algorithm or set of rules. Okay, so let's look at the example that I've shown you in 2D where diffusion is the main thing that's happening. So we'll have two types of agents. At first they're not going to, the first example I'm going to give you, they're not going to interact with the environment at all. And the only difference, which is what you saw in that little demo I showed you, is they only differ in color and they move around randomly. Now, if they're going to leave information about where they are so we can build on this model, then that's where render to texture comes in, because rather than, if I was to just say, okay, here's 100 particles with two different colors and all they do is move around randomly, you don't need render to texture to do that. You can simply do another rendering each time in the new positions, update the positions, render again, update it. That's not very interesting. But if they're going to leave information, and in this case they're going to leave just where they've been, then we need something like render to texture or render to some other buffer to leave that information. We're going to do render to texture. Then I can talk about, well, if you're going to render to texture and that information is stored into a texture map, then I can use the shader, in particular the fragment shader, to then diffuse that information around by a little diffusion shader that we'll see. Now I'm talking about buffer ping-ponging, because I'm going to use the texture that I generated in order to generate a new image and a new texture that I'm going to store, and I'm going to swap the buffers around and go on with this diffusion process. So you see something like this, which is just two snapshots of what I just showed you. Here's the 100 particles, and there's some initial positions, and here they are after they've been diffusing around a while. So you see areas that they haven't visited yet. You see areas where both of them have visited and it turns kind of grayish. Areas where only the one type, the green particles, have been, and areas where only the magenta particles have been. So let's look at the code for that. Then we can talk a little bit about how we change it so the particles can interact with the environment or with each other. Okay, so first I think it's pretty clear that we need at least two program objects. It turned out to be exactly two. We need a fragment shader and a vertex shader for rendering a particle in a new position when it moves around randomly. So for now, they're not going to look at the environment. They're just going to move in some sort of Brownian motion randomly in some direction. And then we need one for what do we do with the texture map when we diffuse it. We need a separate vertex and fragment shader for that. The initialization is pretty much exactly what we did in the last couple of lectures. We set up some empty texture objects. We set up an empty frame buffer object to get started. We distribute particles in random locations around our two-dimensional space, and then all the action is going to occur in the render loop. So there's setup, then rendering is going to just go and do the buffer ping-ponging and redisplay itself. Okay, so let's look at first at the vertex and fragment shaders, and then we look at the application code. So first set of shaders is just for rendering the particles. Well, this one I'm sorry is rendering with a texture. So what does the vertex shader do? It simply passes on the texture coordinate and the position to the rasterizer, and there they go out. The texture coordinate goes out as a varying variable, and we set GL position and send that to the rasterizer. So that's absolutely standard. Likewise, here's the diffusion. So I put them in fragment shader 1, managed to misspell fragment on the top. So here's the fragment shader. Now what is it doing? It's taking the texture that I put in. Okay, now that's initially going to look like my background, but it's going to, if it has something in it, it's going to take the values that are a distance d above where I am. So there's an x and y, and they come back to me from the texture coordinates. Now what we're doing in this example is the texture coordinates are exactly the position inside of that rectangle. So I have the x and the y. I'm just going to put them in these two variables to make the code a little clearer. So I have the x and the y that are my texture coordinates that come in from the rasterizer. I then look at the texture of a point above me at distance d, a point to a point to my right at distance d, a point above me at distance d, a point to my left by d, and a point below me by d, and I sum them all up. So I'm taking the average of the points around me, and I'm making the color be that divided by some scale factor that I can pass in. So it's just to keep the values in the range that I want to see. I want those colors to look distinct, so I pass in a value S, and likewise I pass in this value D, which normally is the distance, should be the distance between two pixels in my space. So that depends on the resolution that I'm using for this application, and D should be essentially 1 over that resolution, and I'll pass that in so I can run this program with different size windows. Okay, so that's the first set of shaders. The second set I probably should have done first. This is the shaders you use for rendering the points. So you're going to set the point size, which will come in as a uniform. I want to be able to make the particles bigger or smaller when I render them, and you're going to set the position to be into GL position, pass that on to the rasterizer, and use a uniform for the point size, so that'll be set in the application. Okay, the fragment shader is totally trivial. It's just the color that I send in as a uniform, and for the first half of the particles I'll send in magenta as the color. For the second half I'll send in green as the color. So those are two pretty simple shaders, sets of shaders. Now what about the rendering? Well, the rendering isn't hard, but there's a bunch of code that goes in it, and I'll go over that pretty quickly. Since we're going to be doing ping-ponging of between two buffers, two different textures, I need initially to set up two different texture objects. So here's where we're setting up two rendering contexts. We're setting up, so we're going to use this flag variable to go back and forth between the two. It's just a Boolean that's going to be true or false. In one case, I bind the texture with texture 1. In the second case, I bind it with texture 2. I set up a frame buffer object with a color attachment, which is a texture, and this is telling it I want to render into texture with texture object 1. Here I'm using texture object 2. So I'm binding the texture in here. I bind it to texture 2, render into texture 1, and the opposite up here. Okay, I set up a frame buffer object before I do that, and then decide which one I'm going to use. At the end of this, I'm going to render just a triangle strip with 4 vertices, which is putting out that rectangle, which this texture map will be used for. Okay, here's the rendering of the points. That's going to be pretty straightforward. I use the second program object that I just gave you. I send the okay, what am I saying? I'm sending here. Okay, I'm sending the points over. The first half of the points, the second half of the points are going to be set into the buffer. So notice that I'm using a buffer that has the size of this buffer is the size that I needed for the original rectangle. Okay, so I sent out a rectangle which is getting texture mapped onto it. That took up 32 bytes for the vertices, and all of these others, the number of points times 8 bytes for each point, is now going to then go into the same buffer after those first 4 points that I need for the rectangle. You can use 2 separate buffers if you want. So here's now generating the bitmaps, binding the frame buffer. Now we're returning to a normal render here. When I do GL bind frame buffer null, that says go back to the default frame buffer, which is the one that you see displayed. Choose which texture you want to use to do that rendering. That's going to depend on that flag variable that I set. Here's deciding this is now setting an appropriate viewport given the size of the window that I'm using, which is 1024 by 1024, divided by the size of the texture, so I can change that if I want. And here's just a normal rendering with the texture. Now I use program 2, so this renders the background. Okay, this just renders that diffused texture that I generated by the buffer ping-ponging. Now here I generate the points as I just render the points. Half of them in red, half of them are green, and that's what you see them here. They're moving in a random position. This is the conversion from the texture coordinates to the coordinate system of the object space. And here now I'm sort of playing around. Oh, this down here, what this is doing is saying what happens when particles go off the end. Eventually, the particles move around, and randomly they'll go over the top or out the right or left or through the bottom. So what I do is I just wrap them around. I say, okay, if you went out on the right side, so the value got bigger than 1, what I'm going to do is just bring it back on the other side. So they wrap around, so I always have the same number of particles displayed. Then I put these vertices back into the buffer that I set up. Now, notice here that important thing is that you are, in some sense, being a little inefficient, because if I have to keep changing where those particles are in space, that means I have to come back, at least the way I'm doing it here, to my application, then change the values of where those vertices are. Well, now I have to send them off to the buffer again. So I use buffer subdata to replace where those vertices are in the previous iteration by the vertices in the next iteration. So each frame I'm sending over the positions of 100 particles again, while all of what I do with the textures is being done exclusively within the GPU. Now you can try and be a little tricky here and try and store vertex positions in another texture which lives on the GPU side and not do this. But this is a fairly straightforward example that I wanted to keep as simple as possible. And then at the end of this rendering loop, we're going to swap the buffers, and we do that by just changing the flag from true to false or false to true, and just generate another, and then call myself recursively to go through this loop again. So that's what you saw over in our example. What if I now want to add a little bit of behavior? And the only behavior I'm going to do is the following. So what I'm going to do is I'm going to move around randomly, and each agent is going to check the background where it's located. It's going to look at the color in that texture and say, oh, if it's green, if I'm a green particle, and I see something that's green there, what I'm going to do is move to the sort of collection point 0.5, 0.5. This is a very contrived example, but it has pretty much the elements of that ant simulation. So everybody who sees a green component over halfway green, I'm going to move to 0.5, 0.5. And then all of the magenta particles are going to look at the red component, because if it's magenta, it's going to have both a red and a blue in it. And what they're going to do is, if it's over halfway, they're going to be moved over to minus 0.5, minus 0.5, kind of diagonally opposite. And then from then on, they're going to move randomly around, so they can wind up someplace else and then be maybe pushed back there. So you should see kind of a collection of greens around 0.5, 0.5, and a bunch of magenta particles collecting around minus 0.5, minus 0.5. I'll show you the example in a minute. Now, so how does the code change? It doesn't really change all that much. Basically, all I have to do, if you look at the previous example, here's the random motion. Now I have to look at what's there. So here's a read pixels of 1 pixel at the point that I'm at, and I put it into color, and then I check the first component, the red, if it's greater than 128 for those particles, for the first half of the particles, and if it's greater than 128, just change the position. Likewise, for the second half of the particles, I check whether it's green by looking at the second component of the color that I read, and if it is greater than 128, I move to minus 0.5, minus 0.5. This is all in the application code, incredibly simple. So here's a little example. I'll show you this more dynamically in a minute. Here's 2 snapshots of that. So in this case, they're just moving around randomly, not kind of not doing very much. Nice pattern, but there's no obvious behavior with the interaction with the environment. In this case, notice that even though you still have all this randomness going on, the greens are tending to cluster around here, and the magentas are tending to cluster around here. And I think from that you can really see just so many other ways that you can put in interesting and complex behaviors, model all kinds of different phenomena by this very, very simple model, and see them graphically. So let's look at it, just finish up by looking a little bit at the examples that I showed you. So let me switch over to this. And here's this example's been running for a long time. Here we go. This one's been running for quite a while, and notice it's turned these areas kind of black, and the greens. It's a beautiful display. This is kind of a neat little screensaver, if nothing else. Okay, let's look at this one where I think they're moving. Let's start this one again. And I think in this case they're going to be moving to 0.5, 0.5, and minus 0.5, minus 0.5. Yeah, you can sort of see this cluster building up here. You see, and if they don't really get above that value, nothing much is happening, and they're just going to wander around here. But eventually, if you follow one, you might see where they sort of stop moving in a certain area, and they're zipped over to one of these collection points. If you look at this version on the website, I think in this version, I just move them to the axes. So here you see an example where if one of the values, I forget what's green, you'll see whether green or magenta. One of them, if they get over halfway, they're snapped over to the x-axis, and for the other color, they're snapped over to the y-axis. So you should see them building up along either this axis or this axis as time goes on. You see a little bit of that here, but it's not. I should have started this a while ago and let it run for a while. But you can run these simulations yourself. They'll be different every time because the random number generator will be seeded differently each time. So that really should open up doors to a lot of things. Just think about how the code really wouldn't be much different if underneath this was a terrain that was modeled by polygons, and now you had to have those particles moving along the surfaces defined by those polygons. You'd have a very more interesting sort of game-like kind of behavior, but it wouldn't be much more complex than what we did here in this example. Okay.